Induction Notes, page 2. So here I have a loop that I'm going to push into a magnetic field. And as I'm doing that, you can see the number of field lines inside the loop is increasing. Those number of field lines is called the flux. We're increasing the flux, which is going into the page. Faraday's law says when we're changing that flux, we're going to create an EMF and a current going through this loop. And we have to figure out which direction it goes in. That negative sign is Lenz's law, which says the current's going to go in the opposite direction from the right-hand rule because it wants to oppose that motion. So instead of increasing the flux into the page, Lenz's law is going to increase the flux out of the page. It's the opposite. So for the direction, I'm going to grab the loop, the right-hand rule, with my fingers on the inside of the loop because that's where the field is, and I want it coming out of the page. And my thumb is showing the direction of the current is going to go clockwise. What is the direction of the force on that current? So if I draw in my current going around like this, now I have a current moving through a magnetic field, and we're going to use our right-hand rule number 2. So let's look at the bottom side first. My current is going to the right, and the field is crossing into the page, and that gives me an upward force acting on my wire. The next section on the right side, the current's going upwards. So I have my open hand current, it's I cross B. So I'm crossing B into the screen, and my force will be to the left for that one. And then the top one, open hand direction of the current, we're crossing towards the field, and the force is going to be downwards for that one. Looking at my net force, those two forces are equal and opposite, so they're going to cancel each other out. So my net force is this one right here, which is opposite the direction that I'm pushing. And that's what Lenz's law says. It's going to create a current that opposes my change in flux. So what is the magnitude of that EMF? We're going to use Faraday's law. It's the change in flux divided by time. I don't need the n on there because there's only one loop, and I don't need the negative sign because I've already figured out the direction. So flux is the amount of field inside the loop, which is going to be the area times the field. And I'm going to break down the area into length times width because it's a rectangle. And I have to remind you that it's not the entire length. This part is not in the field, so that's not changing anything. We're looking at the field lines that are going through the loop that are inside. So we're cutting it off right here. So this from the width goes from here over, and then the length goes here up. Right, now I can do a little math tricks here. I know the change in distance over time is velocity. So I end up with an equation of BLV. B is the field, L is this side of the loop that does not change, and V represents these sides that are changing. End of notes.